Hey there, this video is for learning intention number 14, which is finding derivatives with absolute value functions. So what I'm going to do in this video is give you an example of the procedure involved with the absolute value function, y equals the absolute value of x, and then in the next example we'll do one that's a bit trickier. These aren't hard problems. They require a couple extra steps though. That's the thing to know about them. They use stuff you already know, and the only real thing to look out for is the domain. So whenever you see a derivative of an absolute value function, make sure you're very careful with your domain. Apart from that, it's pretty much a procedure. So a question might look like, given y equals the absolute value of x, find dy dx. Alright, notice previously we didn't actually give a standard derivative for this, or a basic derivative for this. You're going to have to do it using piecewise functions, or hybrid functions. So the first thing I want to do is a quick sketch of the absolute value function. I'm going to give you a sketch over here so we have something to reference when we're doing our algebra. So the absolute value function, you know it well. It looks something like this. There's the absolute value function. And you can see from the graph that here the gradient, if this is y equals the absolute value of x, here the gradient is -1, and here the gradient's 1. So I'm going to take it one step further. I'm going to sketch in what the derivative function looks like. I'm going to sketch it in green. So if that's the absolute value of x, the derivative function starts, it's a line at -1, then it pops up to +1. And the derivative doesn't exist at that point, so my derivative function needs empty circles there. Alright, so that's dy dx. Well, we did that with a picture. How do we do it in algebra? And I'm going to show you how to do that. First thing to do is to describe this as a hybrid function. Hybrid function looks like this. Y equals x if x is greater than or equal to 0, or it equals -x if x is less than 0. That's just another way to write the absolute value function. This is more compact notation. This is showing what's actually going on. I'll show you with an example. Let's say we let y equal 2. Well, over here, we check our domain. Well, 2 is not less than 0. 2 is greater than 0. So if 2 is greater than 0, we let the answer equal x. Sorry, that shouldn't say y equals 0. Sorry, hang on. We're letting x equal 0. Let me start again. So if we're letting x equal 2. Alright, starting again. So let's let x equal 2. 2 is not less than 0. 2 is greater than 0. If x is greater than 0, we take x. So if x equals 2, y equals 2. That's what the absolute value function would do. Let's say we let x equal -3. Well, -3 isn't greater than 0, it's less than 0. So we have to sub it into this bottom part here. In that case, y equals negative, open bracket, -3, which equals 3. So this piecewise function operates exactly how the absolute value function operates. Let's take this derivative. dy dx equals it's a piecewise function, you take the derivative piecewise. The derivative of x is 1. The derivative of negative x is negative 1. Now, the thing to be watching is your domain. Over here, we're not including 0. So dy dx equals 1 if x is greater than 0, and negative 1 if x is less than 0. Notice how the domain's different. And in fact, what we're going to find is that the domain is greatly different with another example. So I'm actually going to stop this here. I'm going to call this video part 1. That's our answer right there. That's an algebraic representation of the green part. Make sure you get this down. In part 2, we're going to do a trickier example. And if you have been, thank you for watching.